Okay, so welcome in this next session of today's class. So in the previous session, we discussed about the binomial probability law, and this is the page where we actually stopped because of the time limit. So let me carry the discussion forward with detailing what Poisson distribution, Poisson probability law is. So what we discussed is that there are some situations under which a particular probability distribution tends to follow another probability distribution. So binomial probability law tends to follow Poisson probability law if the number of experiment is too large and the corresponding probability of success is too small. And this is the formula. The derivation of this particular formula is actually not required. Now, first of all, the parameter of the Poisson variable is given to be lambda. And you know the parameter lambda is nothing but the product of the number of experiment and the probability of success. And once you know this product, the rest of the thing which is present in the formula, that is exponent and x is your choice, x is your observation, how many times it is happening, and exponent of something is actually a constant quantity. So only parameter which is required to get the probability is actually the lambda. That is the first thing. So I have here Poisson probability, Poisson law has got a single parameter. Binomial law has got binomial probability has got two parameters, and Poisson probability has apparently got one single parameter. Apparently, the word apparently I'm actually saying is because in the formula of lambda, the product n and p is hidden. Now, let us first try to understand what do we mean by this n tending towards infinity and p tending towards 0. Define such a situation which is not very common and which is where if you define a success, it's very rarest of the rare to occur. Try to imagine the college. You have already visited our college. Try to imagine the ground which we have in front of our building, the green grass, the lawn where students actually play. And every day in the evening, you actually stroll around the ground. Okay, evening stroll. Every student, say for example. Now, if I ask you, what is the probability that while strolling in this particular field, a particular student will get a snake bite. Okay, so snake bite. He will die of snake bite, or he will get a snake bite. You know, in our building, such a scenario, in our campus, such a scenario is very rarest of the rare. Even if he gets a snake bite, he will not die. Okay, so because that type of snake is not heavy, I think it's not present in our campus. Who never knows? See, it's a situation which is, you can say, anybody can say it's a very rarest of the rare, but it doesn't remain rarest of the rare if you go to a jungle. It doesn't remain rarest of the rare. So the situation which is rarest of the rare in our case, it doesn't remain rarest of the rare in the jungle case. So in the rarest of the rare scenario, if you want to get this success, now I'm saying that I cannot help me but to say that in this current scenario, since I'm interested in snake bites, so I'll say the person getting snake bite is the success. So the probability of success here is very poor, and to get a very minimum probability in this case. We have to repeat our experiment. We have to repeat our experiment. I don't know how many times. You are not sure about it. Okay, I don't know. You do not have any idea how many times you have to repeat, for how many years you have to observe the thing to get one success. That's why that when we are not sure about the number of times the thing should be repeated, that is denoted by n tending towards infinity. So under these conditions, two conditions, a binomial probability tends to follow a Poisson probability. Now let us get back to the previous problem. In the previous problem, I applied binomial probability law very smoothly, but I forcefully applied Poisson probability law, because as I know that binomial probability law and Poisson probability law, they are connected to one another. And it looks like we know everything about all the parameters are known to me, because lambda is nothing but n into p. And since I know np, so I forcefully applied the binomial, Poisson probability law to the given problem. But students answering the question in the examination, where 5 MCQs are there, five questions are there with 3 multiple choice options, and he's guessing the answers, is not a rarest of the rare case. It's not a situation where we have to take n towards infinity. So the situation where I applied this thing is not falling under the category of Poisson probability law, although I did this calculation forcefully. And therefore, I got this different answer. But if there were a situation which at the same time follows binomial law and at the same time it satisfies the characteristic of the Poisson law, maybe the answers will be very similar to one another. But it is better, since the two laws have been designed separately, although they are connected with one another under some scenario, it is better to apply the appropriate probability law to the appropriate situation. Okay, so just don't, we know the probability laws, and we can apply it anywhere. This is not the scenario. So your confusion, I'm trying to eradicate your confusion, that you shouldn't be confused. Now, as you know what should happen, you have to discard this probability and try to retain this one, because this is more appropriate to the examination system problem. Now, some analysis on the some analysis which can be done on this Poisson probability law. The Poisson probability law can be set in another form that I must also discuss. This is the form which I have written over here, is actually very appropriate in the study of queuing theory. Queuing theory is the waiting line theory. Nowadays, you are actually going to the vaccination center to get yourself vaccinated, and you stand in front of the queue. You stand in the queue to get vaccinated. So this queue, this waiting line also goes by a mathematical law. That mathematical law, in there also, the Poisson probability has a very special significance. So in terms of queuing theory, some books you may get the Poisson probability law is written in the following manner, where you see e to the power minus x or minus np, in place of that we have, it is written minus lambda into capital T, and in place of lambda it is written lambda into capital T. So some changes have been made over here. I will not ask you, I'm not asking you to study this particular box section, because I have just put it in the note just to let you know, because in the subsequent semesters you will study queuing theory in some time. So you can then correlate that what we have learned now about Poisson probability law with what we'll be learning in that time. So you can, for the time being, you can avoid it. Another problem which I have given here is it's called magnetic storage and combination problem. So you can do it by, you can go through the problem. Okay, so I'm not actually repeating these cases, and another problem has been set here. Try to solve this particular problem by yourself. Okay, all these problems are very relevant. I mean, very, I mean, very appropriate to the physical situations. They are very often we can deal with physical, you can deal with physical situations with these probability laws. One thing which I haven't mentioned over here, let me write on the board, is that what will be the mean and variance of the Poisson distribution? What is the mean and variance of the Poisson distribution? Okay, I don't know whether in my subsequent notes I have written this or not, but I have already prepared a few notes for you. I cannot recall right now, but in this note, this particular answer is not there. So I'm actually writing it. If capital X is the Poisson variable, then expectation of X or mean of Poisson variable is lambda. Variance of X or variance of Poisson variable is equal to lambda. This is a formula. The Poisson distribution is a distribution, is a discrete probability distribution where mean and variance are same. Okay, so it's very important note. You write it down in your copy. It's a very important note. I'm just checking one thing. That's why I have taken my my phone. I'm calculating something. So just give me a minute. Meanwhile, you write whatever you are writing. Now, what I was doing is that I hope you have written the note in your copy. So I'm stopping the share. I'm going back to the note which I was sharing with you. So what I have calculated is that in this particular problem, n is equal to 5 was there, p equal to 1/3 was there. So I calculated np and npq. Np is the mean and npq is the variance. From Poisson's probability laws perspective, np is the lambda and npq should be the variance, which is lambda. But in this particular scenario, npq and np are not coming as same. So actually it is not satisfying the Poisson probability law. In this way also you can justify this particular fact. So Poisson distribution is a special type of discrete probability distribution where you can get the mean and variance to be same. In this way also you can check whether your distribution is following the Poisson distribution or not. Okay, so this is the end with this particular note. Now I'm going to the another note, which is also dealing with probability distribution. It is also a study of probability distribution, expectation, variance, etc. But a new term has been introduced over here. It is called moment. So I will try to discuss what moment is. Okay, what do we mean by moment? So first of all, let us try to go by the definition of moment. Moment about the origin. I didn't solve any problem on Poisson distribution. I have just left the problems for you to try to find out the problems on Poisson distribution and try to do it by yourself. Later, if I get chance, then I can show you at 1 or 2 problems on Poisson distribution. And what do you think? If you can write in the chat box, can I start this note, or it will? Do you want me to show a problem on Poisson distribution? Because the time limit is very short for this semester, and that's why I'm a little bit moving fast. So if you ask me, I'm just giving this I'm just asking you, if you want me to solve one problem on Poisson distribution, then I can, or otherwise I can start this particular note. Whatever you say. Okay, nobody is saying anything, so I can carry forward with this particular note. Moment about the origin. It goes by the definition that the rth moment about the origin of a random variable capital X denoted by the rth moment about the origin of a random variable capital X denoted by mu r prime is the expected value of the variable capital X to the power r. A general definition. For discrete case, this denoted by expectation of capital X to the power r, which we often denote by the notation mu r prime, and it goes by the notation is defined as summation over small x to the power r px. For continuous case, as I have not yet discussed the continuous scenario, this summation gets replaced by the integration. Okay, in continuous probability law, we replace the summation by the integration, and you know, in continuous functions case, summations are actually gets replaced by the integration. This formula you have already used while calculating the variance. Just try to imagine, or try to recall that in one of the formulas you put r equal to 2 and you calculated e of x square. And I told you that e of x square goes by the formula summation over x square into px. So here the general form of that formula is written over here. So by this formula, not only ex square but ex cube, ex to the power 4, everything can be calculated. If you put r equal to 0 in this particular case, okay, so you get mu 0 prime, and by the formula we get summation over x to the power 0 into px. X to the power 0 is 1, and therefore we get simply summation px over x. But you know, since px is our probability mass function, total probability is always 1. And therefore, for r equal to 0, mu 0 prime, it becomes 1. It's a very important result. Similarly, if you put r equal to 1, you get mu 1 prime. And here you get expectation of x to the power 1, that is capital X simply, which is equal to summation over x, small x to the power 1 px. Now that is equal to summation over x, x px, and that is nothing but your expectation of capital X. So from rth moment, you can derive the formula of expectation by putting r equal to 1. And in general, this formula is called the rth moment about origin. Similarly, we have rth moment about mean. So rth moment about mean, we can define in a similar way. But here now, in place of x to the power r, we are writing x minus mu whole thing to the power r. And the variable is considered to be not small x, but x minus mu to the power r, px, the same manner in which we defined e of x to the power r. For continuous case, summation gets replaced by integration. Okay. And I am leaving this for you to calculate, or no, I'm not leaving, because I have already shown this here, that what happens when r equal to 0, we put r equal to 0, 1, and 2 in the formula of rth moment about the mean. Now try to recall the formula. Okay, this is the formula. I'm again showing the formula to you. Mu r equals to e of x minus mu to the power r, which is given by this. Now if we put r equal to 0, what is happening? If I put r equal to 0, you get mu 0, which is expectation of capital X minus mu to the power 0. And ultimately, by calculating this, you are getting 1. So rth moment about mean gives you 1. Rth moment about first moment, 0th moment about mean gives you 1. First moment about mean, it gives you, carefully observe the calculation. If mu 1 equals to expectation of capital X minus mu to the power 1, we can write it as this, summation over x, small x minus mu to the power 1 into px. Now we can take the product of these factors and we can apply summation on each of these factors. So we get this is equal to summation over x, x into px, minus mu into summation over x px. Now so total probability is 1, so this becomes mu only. And summation x into px is also expectation of capital X, which is mean by the notation. So you are actually getting mu minus mu, which is 0. And similarly, if you do the calculation, if you put r equal to 2 in the rth moment about mean, you will, and by the similar calculation here, which has been shown explicitly, you can get that the second moment about mean is nothing but equal to variance of x. So these questions may be asked in the online examination in MCQ types. So you have to remember the results. Okay. Now the formula which I'm writing over here, this formula is already known to you. In the previous class, I have already discussed that. Although I'm I'm reading this out for you in a formal way. So if capital X is a discrete random variable, the function given by Px for each x within the given range of capital X is called the probability distribution. And the probabilities satisfy the following properties, which is Px greater than or equal to 0 and summation Px equal to 1. For discrete random variable, I am going to define another important thing now. You know this particular probability for laws for this particular PMFs. Here I'm going to define another important function, whose definition goes like this. If capital X is a discrete random variable, the function given by capital Fx, is equal to probability of capital X less than or equal to small x. This probability, all such values of capital X which is less than or equal to small x, Okay, we add them together. That function is denoted by fx and is defined by summation pt. I'm introducing one another variable t, where t is taking values lesser than or equal to x. T is ranging from minus infinity to plus infinity, where pt is the value of the probability distribution of capital X at t. Is called, this type of function fx is called the distribution function or cumulative distribution of capital X. Cumulative distribution is also a kind of function which often helps us to identify a physical system satisfying certain probability law. A balanced coin is tossed 4 times. List the elements of the sample space that are presumed to be equally likely, as this is what we mean by a coin to be balanced. And corresponding values small x of the random variable capital X is the total number of heads. Okay, now just like our previous digital transmission signal problem, total number of outcomes in this particular case will be 2 to the power 4, which is 16. So here also I have tabulated all the outcomes. I have highlighted them. Since I'm saying that the coin with which I'm tossing is balanced, all the outcomes have been assigned equal probability, which is 1 by 16. And I'm counting the number of heads in each of these outcomes. So here for this, I'm getting the number of heads to be 4. For this, it's 3. For that, it is 2. And in similarly, lastly, we get H for HTTT, for it is the number of head is 1. And lastly, for TTT, we are getting the number of heads to be 0. So all the outcomes have been tabulated. Now we are supposed to find the formula. We have been asked to find a formula for the probability of total number of heads obtained in 4 tosses of a balanced coin. Now from the table, it is very easy to see that probability of x equal to 4 is 1 by 16. That means 4 heads is appearing. Probability of x equal to 3. Okay, let us try to see. Probability of x equal to 3 means only take this value, this value, this value, or this value. That means you can take that value or this or this or this. So if I do this, how many 16s we are getting? 4 16s we are getting. So in this manner, for probability of x equal to 3, I'm writing 4 by 16. Probability of x equal to 2, I'm writing 6 by 16. Probability of x equal to 1, I'm writing 4 by 16, and that is 1 by 16. If I observe the situation very carefully, I will get that probability of x equal to small x is actually satisfying a certain formula. You can represent all the probabilities by a formula, which is 4cx by 2 to the power 4. Put x equal to 0, 1, 2, 3, 4 over there. You will get each of these probabilities. So the probability, this function which we have obtained is called the probability function. Now, since the values are discrete, because the number of counts of heads are discrete always, so this is a discrete probability distribution. It is not a binomial probability law. This is something else separate, a probability law. Just imagine a probability law has been considered. Now, what is distribution function in this particular case? I have actually written this particular problem just to let you know what is distributed, or how to calculate the distribution function. Once you get the probability law, which is given by this for a certain problem, the distribution function for the same problem of the total number of heads can be calculated in the following manner. A distribution function is given by this formula, you know, fx equal to probability of x less than or equal to small x, which is summation over pt, where t less than or equal to x. Now f of 0 will be probability of x less than or equal to 0. Now, probability of x less than or equal to 0 means if I apply this formula, it is summation over pt, t less than or equal to 0. Only one possible value for t is 0. So I am putting over here p of 0, and which is 1 by 16. When I'm calculating f of 1, so by this formula, I'm writing probability of x less than or equal to 1. By this expression, I'm writing summation over pt by where t less than or equal to 1. Now, the discrete values which t can take are t equal to 0 and t equal to 1. No other possible cases are there. So for probability of 0, it is 1 by 16. Probability of 1, it is 4 by 16. If I add them together, we get 5 by 16. In a similar manner, we can calculate F2 and we can calculate F3, and we are getting these values. Okay. And lastly, we are calculating F4. When you are calculating F4, the value which is coming out is equal to 1. This means that in the probability function, you have considered all possible values of the sample space. All possible probabilities have been considered. If your distribution function, final value of the distribution function at certain point is not coming as 1, that means you have done something wrong, or your probability distribution or probability chart is incomplete. So distribution, the last value is of the distribution function at certain point is equal to the total probability. Okay, you have to remember this result. And you can organize your distribution function, because we have written here in a very crude manner. So this is the calculation part. So you can organize this in a very suitable way in the following manner. So for example, fx, when small x is less than 0, no such value is there present in my calculation. So I have put here 0. When x is lying between 0 and 1, now see, I have included 0 over here, 1 is excluded. The probability which I calculated is 1 by 16. When x is lying between 1 and 2, the probability which I have calculated is 5 by 16. Probability which I calculated here is 11 by 16, and so on. And ultimately, lastly, we are getting probability of when x greater than or equal to 4 is 1. So in the following manner, these probabilities have been, this distribution function has been arranged. Okay. Try to do the problem by yourself without looking at the solution once. If you are facing any trouble, in the next class, we can again discuss the distribution function, because distribution function is very important. Distribution functions have certain properties. The values fx of the distribution function of a discrete random variable capital X satisfy the following properties. For extended real number system, if you include minus infinity and plus infinity, the value of the distribution function at both of these points are as follows. At minus infinity, the distribution function is considered to have value 0, and at plus infinity, it is considered to have value 1. If a less than or equal to b, distribution function of fa is less than or equal to fb for any real values a and b. And there is a theorem which I'm not going to do. I'm going to solve this problem on the basis of this theorem, not in this class, because I think it is too much for one day. I shall conclude my today's session with this theorem only. You go through the notes, which I'll be uploading in the Google Classroom very shortly. That if the range of the random variable capital X consists of the values this, then probability function at the value x1 will be same as the distribution function at the point x1, and probability function at the value of xi, all the other subsequent values, can be calculated using the distribution function values at this point. So f of xi will be equal to capital F of xi minus capital F of xi minus 1. This theorem is very important. I shall explain problems on the basis of this theorem in the next class. Okay, so today I'm going to conclude at this particular stage, and I'm going to upload the video in the YouTube very shortly. I'm actually engaged in some other activities in today, for which I'm a little bit of, disturbed, like there's a meeting after this class, and then I have to take a CA1 examination of the second year students. So therefore I have to conclude at this point. Okay, so various types of activities are actually coming in very fast. We are given very short amount of time to deal with those activities. So in the next class, that means tomorrow, we are again going to deal with the distribution function. But I ask you to go through this particular problem and do the calculation by yourself, and try to define, don't look at this form, and try to define this function, distribution function, by yourself. If you face any trouble, tomorrow you tell me, and I'm again going to explain the situation to you. Tomorrow, I have class with you. I cannot remember right now. If I have a class with you, then CSE section B, yeah, at the same time, at 1:40, then we can discuss with this. Okay. So now I am going to end my session. Thanks for joining, and you have scored very well in the first CA1 examination. 1 or 2 students are there whose score was not very good. I don't want to take their names. Other than these people, rest of the guys have got very good marks. Okay, and that marks which we have got and which I have sent you in the WhatsApp, you have already viewed your score. That mark will be sent to Knockout. Okay, so with this, I'm going to conclude my today's session.